Hello everyone, welcome back to my channel. My name is Ankit and today we are going to learn complete networking from scratch. This course is specially designed for beginners as well as DevOps professionals who want to learn about networking. In this course, we are going to cover OSI model, TCP/IP model, IP addressing, subnets, ports and protocols, and other cloud networking components. By the end of this course, what you can expect. So you will get an overview of all networking concepts required for IT engineers as well as DevOps professionals with real world example. After watching this complete course, you can easily understand, design, manage, and create your own networks. So without further delay, let's get started. So we'll start with one real world example which represents how OSI model is used in real world. OSI model is basically a logical model in order to represent how data is being transferred over the internet. Here, the example we are going to see is Amazon search example and user. In this example, we have a user who is searching for iPhones and on Amazon's website. So here input data is iPhones and data is being processed, translated, fragmented, encrypted by OSI model in order to send it over the network. Once the user input data reaches to Amazon server checks if there's any matching entry for that input data in their database. If they found results for that input data, which is nothing but iPhones in our case, they sends the result back to the user. The next step in this particular process is the data is sent back to the response data is sent back to the receiver. So when a response data from Amazon server is sent to the user, response data is processed by OSI model in the reverse order. So how OSI model works in this particular scenario? So when user acts as a sender, input data is processed from application layer to physical layer and sent over the network. But when user acts as a receiver, response data is processed from physical layer till application layer, and then response data is rendered in application. So let's see what all layers are there in OSI model, how this layer works, and let's start with OSI model and TCP/IP model. OSI model is the logical model, and it is used to represent how data is being transferred from one device to another over the internet. This whole process is divided into 7 layers, and each layer has its own roles and responsibilities. So let's go through these layers one by one, starting from application layer. And as we have already demonstrated in previous example, when user act as a sender, input data is processed from application layer to physical layer. So in this particular case, the data which is sent by user is being processed starting from application layer till physical layer. So application layer is a layer where user directly interacts with the application. The first layer in the OSI model is application layer, and this is where user directly interacts with the network. So this layer is responsible for providing network services directly to end user applications. You can think of web browsers, social media apps, or e-commerce app like Amazon. So this is where they operate. For example, in our previous example, a user wants to buy iPhone from Amazon. So what he has done, he has searched on Amazon website for iPhones. So this is the function of application layer, and protocols used are HTTP, HTTPS, SMTP, and DNS. So these are the commonly used protocols at application layer, and the devices which are being used at application layer are smartphones, then laptops, etc. The input data from input data, which is nothing but iPhones in this particular case, is sent further to presentation layer. So next layer in the OSI model stack is presentation layer. As name itself suggests, presentation layer is responsible for presenting your data in a standard format. So your input data, which is nothing but iPhones in our case, is presented or formatted in such a way that receiver can understand. So receiver is nothing but Amazon.com, or Amazon server is receiver in our case. And it handles, this particular layer handles encryption, compression, and translation of data into standard format that devices can read. And the protocols which are being used at presentation layers are SSL, TLS, JPG, GIF for image data, ASCII, UTF-8, UTF-16 for text input data, and MP4, MKV for video files. So these are the standard formats which are being used to format your input data at presentation layer, and it also performs encryption and decryption on input data or response data respectively. So encrypted data or formatted data is further sent to the next layer in the OSI model stack, that is session layer. Session layer is the third layer of OSI model stack, and it is responsible for managing sessions between user and Amazon server. It ensures that connection stays open and active while data is exchanged, and it can restart the connection whenever it required. So protocols which are used at session layers are NetBIOS and RPC. In previous example, we have seen that user sends request to Amazon website, but in order to do that, user has to be authenticated with Amazon website. And when user gets authenticated with Amazon website, a session will be created by Amazon server. That session will be maintained by Amazon server. Once the session is gets expired, then user has to re-authenticate in order to work with Amazon. So session management is basically done at session layer. Your input data is further sent to next layer in the OSI model, that is transport layer. So application layer, presentation layer, and session layer, all these three layers deals at your browser itself. The next layer in the OSI model stack is transport layer. Transport layer ensures complete data transfer with flow control, error detection, data recovery, and data integrity using protocols like TCP and UDP. TCP stands for Transfer Control Protocol. UDP stands for User Datagram Protocol. So in transport layer, your initial data iPhones gets divided into chunks, and each chunk is called as segments. Segments will get added with some headers like port number, sequence number, and checksum. So application layer is the first layer where user directly interacts with network using applications. So applications like browsers comes into picture at browser, apps, etc. This layer provides interface to user, and the protocols which are being used at this layer are HTTP, HTTPS, SMTP, DNS, etc. The next layer in the raw input data is further sent to the next layer in OSI model, that is presentation layer. Presentation layer is responsible for translation and encryption of your data. Encryption of your data. So translation into a standard format, into standard format translation into standard format, and encryption of your data. Protocols which are used at presentation layer are SL, TLS. Then it makes use of standard formats like JPEG, PNG for image data, ASCII for text data, etc. That translated and encrypted data is further sent to session layer. So session layer is responsible for managing the session between user and destination server. So in this case, a user is uh, one who is who is searching for iPhone, and destination server is Amazon, and connection will be made, and it will be kept open until your session is active. So session layer is responsible for creating, managing, and validating your session. Creating, managing, and validating your sessions. The protocols that are being used at session layer are NetBIOS, RPC, etc. Next layer in the OSI model is transport layer, and it ensures complete data transfer with flow control, error detection, data recovery, data integrity, using protocols like TCP and UDP. TCP stands for Transfer Control Protocol, and UDP stands for User Datagram Protocol. So these are the two protocols which are being used at transport layer. TCP is connection oriented, UDP is connectionless, and TCP ensures a complete data delivery, whereas UDP is faster but it is less reliable because it does not guarantee a complete data delivery. So TCP is connection oriented and UDP is connectionless, and it ensures data delivery in correct order, faster, and does not guarantee complete data delivery. Faster but unreliable. And UDP is basically used for streaming purposes. So if you are live streaming, or if you are using, if you are gaming, then in that case UDP protocol is used. TCP is for connection oriented data transfer. So when you are transferring any data, or when you are transferring any video, like data which is critical, then in that case you will use TCP. So these are the two protocols which are being used at transport layer, and transport layer is responsible for segmentation. So your data is divided into chunks called as segments. So your input data is divided into chunks, and each chunk is called as segment. So what all information segment stores? So segment stores payload, which is nothing but your input data, and some headers. So these headers gets added at transport layer. So what are headers transport layer adds to this segment? There are three main headers that gets added. First one is port numbers, source and destination port number. Second one is, the first one is source and destination port number. Second one is sequence number, and the third one is checksum. So port number, source and destination port number, where uh, your data will be sent. To send data in correct order, sequence number are used. Then first one is to where to send data. So these are the port numbers where your data will be sent. And checksums are for error detection. So if there is any error, your data will be retransmitted. So these are the main roles of transport layer. And the output of transport layer is segments, and these segments are further sent to network layer, which is fifth layer in the OSI model stack. And the next layer in the OSI model stack is network layer, and network layer is responsible for ensuring routing of data between different devices across network. Network layer receives segments from transport layer and transform those segments into packets. So segments will be transformed into packets at network layer, and this packet will add few more extra headers like source IP and destination IP. So in this case, a user IP will be stored in source IP, destination IP will be the IP address of Amazon server, and this information will get added to packets. This layer ensures that your packet your packet finds the best path to reach destination server. So in our case, it is Amazon server. So protocols that are being used at network layer are internet protocol, internet internet control message protocol, ICMP for error detection, then ARP for to resolve IP to MAC address. So these are the commonly used protocols at network layer, and packets are further sent to the next layer in the OSI model stack, that is data link layer. So the next layer in the data link, so the next layer in the OSI model stack is data link layer. We have just moved this data for the better visibility to right side. And the next layer in the data, we have moved this, the content here is just to further for better visibility, I have just moved content written over here to right hand side. And the next layer in the OSI model is data link layer. So packets from network layer are further sent to data link layer, and data link layer will ensure that the packets will be converted into frames, and each frame will get added with few more headers like MAC address. MAC address is added to your initial data. So starting from transport layer, your data starts, your input, raw input data gets converted to segments. Further, it converted to packets, and now it has converted to frames. And at each layer, we have added some headers. Like transport layer has added, uh, at transport layer we have added payload, which is nothing but data. Then headers like sequence number, ports, and then checksum. At network layer we have added, so this payload, sequence number, ports, checksum is there. We have also added source IP and destination IP to this address and converted this data as packets. Then next, at data link layer we have added, this payload is still there. Yeah, sequence number, payload, sequence number, ports, checksum, source IP address, destination IP address, and MAC address is also gets assigned, and we call this as frames at data link layer. So data link layer is responsible for transferring your data within a same local network, and common devices used at this layer are Ethernet and Wi-Fi. So the data is transferred data is transferred within same local network, and devices used at this layer are Ethernet, Wi-Fi. This layer also handles error detection and retransmission, error detection and retransmission, retransmit data at link level. This layer ensures that data is ready for transmission. So this is the job of this data link layer, is to ensure that data is ready for transmission. Frames created at data link layer further sent to the next layer in the OSI model stack, that is physical layer. So physical layer is responsible for converting your data into binary format. So data is sent across network in the form of electronic signals or radio waves, responsible for transmitting binary data on network. So frames will get converted into raw binary data into zeros and ones, and this binary data will further sent to electronic, like mediums like cables or Wi-Fi. If it is sent from cables, then it will follow electronic signals. If it has sent from Wi-Fi, then it will follow radio signals. And using this format, your data will be transferred to destination server, and your data will go from multiple routers in order to reach. So this R stands for router, and it will reach to Amazon server. Amazon server will process that data, and if it finds results for that data, then send the it will send the response data back to the user based on the information like source IP, destination IP, port address, and MAC address. So data will further find the same path in order to reach to sender, in order to reach to that particular user, and user it will process the response data in the reverse order. So your response data, your response. So this is request data, input data, response data is further transferred by through OSI model, and when it is processed, when response data is processed, it will be processed in reverse order. So it will be starting from, it will get started at physical layer, and similar functions, similar roles and responsibilities will be followed by each layer in the OSS model, and finally the data gets rendered to user application, that is nothing but a browser. So in this case you can see this. So this is the high level overview which we have shown, and you can follow the similar information right here in this particular layers. So application layer deals at browser layer, so application layer, presentation layer, and session layer deals at browser level. When data is supposed to be transmitted over network, your data gets converted into segments, packets, and frames, and this is the job of transport layer, network layer, and data link layer. Further your data is sent in the raw format Further your data is sent in the raw format using physical layer. Once your request reaches to Amazon server, your request will be processed by Amazon server, and it will generate some response, and that response will be sent further back to the user. And during this process it also follows the similar functions, and it also follows the similar path. So OSI model will first so the it starts from bottom, and the first layer which it will interact while processing the response is physical layer. Then the next layers will be uh, data link layer, network layer, and transport layer. And once the segments are created, it will further send to uh, session layer. Then next one is presentation layer, where your data will be translated into a format which that particular application understands. So uh, it will be translated in the format that Chrome browser can understand. And next one is application layer, and finally your data will get rendered on application layer. These are the main layers, these are the functionalities of OSI model. So if you observe this type model here, it is 4-layer architecture model, and it is used in real world networking, and it is used for implementation of network designing, and it is a compact version of OSI model. So here you can see application layer, presentation layer, and session layer of OSI model is combined within application layer, and the ports and protocols are remain same. The functionality is somewhat remains same at application layer of TCP/IP model. Then transport layer remains same, and TCP and UDP, these are the two protocols which will be used at TCP/IP model as well. The network layer acts as internet layer, and the functionality is remains same. The data link layer and physical layer of OSI model is combined as network interface layer, and the somewhat functionality of OSI model is same as TCP/IP model, but it provides compact version, and it has Uh, it has been designed considering the real networking scenarios. So this is all about OSI model and TCP/IP model. If there are any queries related to any of the layer or any of the example, then you can post it in the comment section. See you all in the next topic of this networking course, that is IP addressing. So let's get started. IP addressing. So IP address is a 32-bit number which uniquely identifies any device in the network. So best example is our smartphone, and each smartphone has a unique IP address assigned by their ISPs. So here you can see the IPv4 address, and that is 192.168.1.2. So you might ask, what? Why do we need this number? What is the usage of this particular IP address? So IP address uniquely identifies my device in the network, and that because of that I could able to access the internet on my device. If I don't have any IP address, then I won't be able to access the internet, or I won't be able to access the network basically. So IP address is basically divided into two parts: network ID and host ID. Network ID is used to identify the network for an IP. So in this particular example, my IP address is 192.168.1.2, and this is the class C IP address, and the network ID for this particular IP address is 192.168.1.0/24. So this is the subnet mask for my network, and this is the network address. So this is the network ID for my IP, and host ID identifies the host for an IP. So the host in this particular case is .2, which uniquely identifies that this is my IP. So 192.168.1.2, here this section is network ID, and this 2 is my host ID. And these are the two main things about IP which you should remember. uh, Next thing we are going to see is types of IP addresses. So we have like different types of IP addresses based on their functionality. So first one is public IP. So to access your IP, or to access your device over the internet, you need public IP. So best example is website or a virtual machine that you have hosted in cloud. So if you want to access VM in your cloud, on your phone or over the internet, in that case you can assign public IP to this particular VM, so that you can access this VM outside your network. This is publicly available. Second one is private IP, and in order to and the usage of private IP is to access devices over the private network. So let's suppose if you want to uh, set up a lab, or if you want to set up a, uh, a secure network, in that case you can create private IPs. So for secure network, you can create private IPs, and this is mostly used in organizations, and like VMs will get added. You can assign private IPs to your VMs, so that you can access those VMs only within your organization. So next type of IP is static IP. These IPs are basically manually assigned to the devices, and these are basically used for specific purposes. And you might have seen mostly in LANs or college labs that we assign some static IPs to the devices in order to access internet within a college or universities. So static IPs are fixed IPs, and these IPs doesn't change unless we do. Next type of IP is dynamic IP, and this particular IP which you are seeing it here is dynamic IP, which is assigned by my Wi-Fi router. And dynamic IPs are assigned automatically to the devices dynamically. In order to assign IPs in a dynamic way, we have a protocol called as DHCP, which follows DORA process in order to assign IPs from free IP pool. So this DHCP and DORA process is advanced networking concept that we are not going to cover in this particular networking course. But you can just remember that DHCP is the protocol which is used for dynamic IP assignment. Next type of IP is loopback IP, and you might have used it a couple of times. You might have seen it earlier as well that we use localhost for experimentation and testing purpose. So if you want to host a website on your personal laptop, then you can use localhost to perform testing of that particular website. So these are the major types of IP addresses that are being used. Next topic is IP classes. In IP addressing, we have two versions of IP addresses: IP version 4 and IP version 6. IP version 4 is 32-bit in size and IP version 6 is 128-bit in size. The number of hosts or number of IP addresses available in IP version 4 are 2 raised to 32, and in IPv6 it is 2 raised to 128. So it is in IPv4 it is somewhere around 4. It is the IP addresses available in IPv4 are somewhere around 4 billion, and IPv6 it's a large number. So a lot of IPs. So basically, a lot of IPs are available in IPv6, and the IP addresses in IPv4 are somewhere getting like there are like this limit is somewhere getting fulfilled in near future, and that is the reason is IPv6 will be used in future. So IP classes, IPv4 addresses are grouped into 5 classes based on their first octet. So this is the first octet of IP addresses. So any IP address that you can uh, guess. So let's suppose uh, if we write down few random IP addresses like 192.168.1.2, 172.16.2.3, then 16.18.19.20, 51.52.53.54. So these are the random IPs I have written, and based on this first octet, you can identify the class of these IPs. So this is the IP from class C network. This is the IP address for from class B network. This is the IP address of class A network. This is the IP of class A network. So these are the classes based on which you can easily identify. You can easily identify or create classes for your network. So we have 5 classes A, B, C, D, E, out of which A to C are only used in real world, and this D and E are reserved and used for specific purpose. CIDR or subnet mask for these IP classes is /8/16/24. We are going to cover subnet mask in the next chapter, and the first octet range for these particular classes is 0 to 127. So any IPs which are within 0 to 127 will be considered as class A IP addresses. Any IP addresses which starts with 128 till 191 number, which will be considered as class B IP addresses, and any IPs which will get started with 192 till 223 will be considered as class C IP addresses. And the private IP, like if you want to use this if you want to use these particular classes for your private networks, in that case what are the IP ranges that you can use? So these are the private IP network ranges for each of this class. So 10.0.0.0 to 10.255.255.255 is the private network range for class A IP addresses. Similarly, for class B, we have 172.16.0.0 till 172.31.255.255. And for class C, we have a private network range starting from 192.168.0.0 till 192.168.255.255. So this is the CIDR or subnet mask for class A private network. This is the subnet mask for class B private network, and this is the subnet mask for class C private network. And based on this subnet mask, you can calculate the number of hosts for this particular private network. So class A has 8-bit SOP network and 24 bits. So IP address is as we have mentioned IP address is 32-bit number. So out of this 32, first 8 bit are assigned to network and next 24 bits are assigned to host. Then first in I class B, we have 16 bits. First 16 bits will be assigned to network and next 16 bit will be assigned to host. And based on this 16 bit, your host will be identified. In class C, first 24 bits are assigned for network and last 8 bits are assigned for host. And based on this network ID and host ID bits, your network will be identified and your end host will be identified. So whenever any data will be sent or received, it will be first received at your network end and then it will be processed to your host ID. So let's suppose I am a this is my smartphone and the IP for my smartphone is 192.168.1.2 and this is the network of 192. This is my network 192.168.1.0/24 and in this particular network we have let's suppose they have 254. So number of hosts that this particular network supports is 255 or 254 and whenever there is any data which so let's suppose my friend has sent some message to me, some WhatsApp message to me, so that message will first gets delivered to router internet some router and through routing it will reach to my network first and my network will decide okay so what is the host ID for your end, so it will check what is the destination IP and based on that destination IP it will forward that data to my device. So this is like high level overview and this sender will also be part of some XYZ network and he will send some message. That message will be routed across the different routers and before it reaches to me it has to reach to my network first, which is 192.168.1.0 and my network will further send that data to my device. So this is how data is being forwarded or sent across network and the common use cases for this particular IP classes is given here that you can go through. Next topic that we are going to cover is representation of IP address. So this is the snippet I have taken from my mobile phone settings and the IP before address is clearly mentioned here. So how we can represent this IP address in various formats that are being used in networking. So we'll have a clear understanding how this IP can be represented. So let's go to the paint and we'll see how we can calculate this binary representation. So dotted decimal, so this IP address which is shown in the snippet is dotted decimal format. If we want to convert this dotted decimal to binary format, then we need to calculate it. We need to calculate this number. So before we convert this number, this dotted decimal into binary format, we'll note down the powers of 2, that is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3 till 2 raised to 7, 5, 2 raised to 6 and 2 raised to 7. The values are 1, 2, 4, 8, 16, 32, 64 and 128. So these are different. So these are the values which, so in order to convert this dotted decimal to binary, we will note down this number. So 192, 168, 1, 2, and these are the powers. These are the power of two numbers which will be used to convert any binary number, any decimal number to binary. And 2 raised to the power of 0 is 1, 2 raised to the power of 1 is 2, till we have written down for 2 raised to 7 till 120. So in order to like we need to use these numbers in order to calculate these values, and 192 is the addition of 128 plus 64, so which is uh, and we'll note down ones. So whichever value we use, we will note down one for those values, and remaining will be treated for remaining places we will add zeros. So for 192, these are the initial two places which will get a value of 1, and remaining will be filled with 0. So for 168, what values we can use? So 128, 32 plus 8, which is nothing but 1, 0, 32, 0, 1, 0, 0, 0. For 1, the last bit is only activated. So 0, 0, 0, 0, 0, 0, 0, 1. For 2, second last, 0, 0, 0, 0, 0, 0, 1, 0. So this is the binary representation of RIP. So similarly, you can calculate any IP uh, with this method. So similarly, you can convert any IP to binary number using this method. And here you can see this is the class C IP address, because first octet is 192, which is in the range of class C IP address, or uh, class C IP address. And you can see it here is subnet mask and subnet mask decimal. So subnet mask for class C IP address is, so subnet mask for class C. So here you can see CIDR, private network CIDR. CIDR is a alias name for subnet mask. So here subnet mask for class network address is 24. So first 24 net bits are represented by subnet mask, subnet mask, and last bits are represented by host ID. So this will fill with zeros, and the network ID will get filled with all ones. And we'll see what is subnet mask in the next topic. Next topic that we are going to cover is subnetting. So subnetting is the process of dividing large network into small subnetwork based on requirements. In subnetting, we have two types of subnetting. First one is fixed length subnetting. So first one is fixed length subnetting, so fixed length subnet mask. Next one is VLSM. VLSM stands for variable length subnet mask, and fixed length subnet mask, which is used in classful addressing. And there was a IP wastage in classful addressing. That is where this VLSM came into picture, and your total IP address space gets divided into subnets of various lengths based on requirements. So your organization may have let's suppose 10,000 IPs. So those IPs will be divided into different departments, like HR will get few IPs, development will get few IPs, then support team will get few IPs, finance team will get few IPs, sales department will have their dedicated like network, and they will be assigned with few IPs. So based on requirements, subnets will be created for each of these departments, and this is the role of subnets. Like this is the role, or this is the major responsibility of subnetting, is to create create sub networks out of this larger network based on requirements. So it is also called as classless subnetting, as we have seen here, and it borrows bits from host ID part of IP address. So in previous section we have seen IP address representation, and here you can see in binary representation we have seen uh, like different in binary representation we have seen ones and zeros. So in subnet mask it borrows bits from this host part in order to create subnetworks, and that we will see with some practical examples. So what are the advantages of this subnetting? So it improves overall IP management. So in classful IP addressing there was a wastage of IP addresses. So let's suppose in classful addressing, if I wanted to create a network with 500 IP addresses, so for that purpose or for that requirement, I had to create a network of class B address, because class C address only creates a network for 254 hosts. So my requirement won't get fulfilled. In class B networks or in class B, in class B network, it provides somewhere around 65,000 IP addresses, which is not a requirement. And after using this, after using 500 IP addresses, the remaining 65,000 IP addresses will be wastage for me. So there was a wastage in class pool addressing. So to overcome that, classless subnetting is introduced, and it improves overall IP management. Like sales team, if sales team wants only 50 IPs, we then network admin or DevOps will create a subnet for 50 IPs only. If HR wants 30 IPs, then subnet will be created for 30 IPs. Likewise, a subnets will be created based on requirements. Then security. So since your whole network is divided into subnetworks, and the isolation will be there, so these subnetworks will work in isolation. So you can apply a security on each of these networks. So you can apply NSGs or firewalls at subnet level. So this also provide security and network segmentation. So your main network gets segmented into multiple subnetworks. So these are the advantages of subnetting. So key terms used in subnetting. So key terms used in this particular topic is subnet mask. So in previous slide you have seen subnet mask. So what is this subnet mask? So subnet mask is the 32-bit number, and it denotes how many bits are used for network ID and how many bits are used for host ID. So here you can see how many bits are used for network ID, 24 bits. How many bits are used for host ID, 8 bits. Network part is denoted by all ones and host part is denoted by all zeros. So here you can see all bits in network ID is denoted with 1 and host ID is denoted with all zeros. And there is one more name to subnet mask, that is CIDR notation. So CIDR notation is compact way to represent subnet mask, and CIDR stands for classless interdomain routing. And the best example of subnet mask and the example of CIDR notation is subnet mask of 255.255.255.0 can be represented as /24 in CIDR notation. So this is the theory part of subnetting. Now we are going to see the practical example of subnetting. So important point to note down here is host ID addresses with all ones and all zeros in binary format are invalid. So you can't use addresses with last octet of 0, 63, 64, 127, 128, 191, 192 or 255. So IP addresses for host So IP addresses for any host can't be from any of these values. So last octet should not have these values. If they have these values, then these are invalid IPs. So important formulas to create subnets are as follows. So number of subnets is equal to 2 raised to the power of n, where n denotes borrowed host bit. And the number of hosts can be calculated as 2 raised to the power of h minus 2, where h denotes remaining host bits. There is a website that you can use to calculate subnets, but understanding the underlying concept is important, and that is the reason we are uh, here and we are learning these concepts. So once you learn these concepts, calculating subnet is a piece of cake, and you can calculate any subnets using this subnet calculator. But for your own understanding, you should know how these subnets are created, what is the underlying methodology to create these subnets. So in order to see that in a practical manner, we have taken 3 examples here, and we'll see how subnets are created for any networks. So in example 1, we are going to take any random network address and create subnet with 50 hosts for XYZ company's network. So first example is take any random network address and create subnet with 50 hosts for XYZ company's network. Let's take a practical view on example 1. Take any random network address and create subnet with 50 hosts for XYZ company. So XYZ is the company name, and the random network address we are going to take is 192.130.2.1.0/24, and the requirement is to have number of hosts they want to create. Number of hosts they want to create is 50 hosts per network. And let's suppose they want to create 4 subnetworks for 4 departments. Number of networks that want to create is 4 for different 4 network departments like sales, finance, support, IT. So these are the 4 departments for which they want to create a network subnets, and the number of each department will have 50 IP addresses. So let's start with calculating subnets. So the formula given here is number of subnets is equal to 2 raised to the power of n. 2 raised to the power of n. So uh, number of subnet is equal to 2 raised to the power of n, and we already have the value 4. So n becomes 2. 2 raised to the power of 2 is 4. So uh, n is the borrowed host bit. So here we will write the 2's power. So 1, 2, 4, 8, 16, 32, 64, and 128. 0, 1, 2, 3, 4, 5, 6, 7. So 7. So here we have written 2's power in order to calculate, in order to convert binary number for this network address. So 192.138.1.0 can be represented as 128, 11, 4 times 6 times 0 dot 132, 128 plus 4, 132. So 1 0 0 0 0 1 0 0, then 1 7 zeros 1, and this is, so this is the network ID. This is the host ID, and from host ID how many bits are we are going to borrow? 2 bits. Borrow 2 bits. Subnet mask for this network is all ones for network ID. 1 2 3 4 5 6 7 8, and this is host, and we are going to borrow these 2 bits from host ID. So the changed subnet mask will be 26. So the 24 plus these 2 borrowed bits, so changed subnet mask will become, so here we have borrowed 2 bits, and now the net mask or subnet mask, the default subnet mask, this is default subnet mask which was 24, and the changed subnet mask or VLSM, variable length subnet mask, will be 26, and the host section will have only 6 bits remaining. 4, 6, and this will have 26 bits now, and this is the variable length subnet mask, and slash 26 is the CIDR notation for this particular network. And what all networks, this is, so far we have calculated number of subnets. Now number of hosts can be calculated easily. Number of hosts, so number of hosts is equal to 2 raised to the power of h minus 2. So here host bits are, how many now host bits are remaining? 6 bits. 2 raised to the power of 6 minus 2 is equal to 64, minus 2 is equal to 62. So this many hosts will be there for each network. So now we have sales team and sales subnet. Sales subnet will have network range starting from 192, 130, till 192.132.1.63. Next is finance team. Finance team will have fin subnet, which will start from 192.132.1.64 till 192.132.1.127. Next is support team. So support subnet will start from 192.132.1.128 till 192.132.1.191. Then IT subnet will have 192.132.1.192 and 192.132.1.223. So these are the networks that will be created. These are the subnets that will be spinned up or created for these different departments of XYZ organization, which has a network address of 192.132.1.0. And in cloud, this is represented as VNet virtual network, and this is represented as subnet. And these are the first one is the network address, last one is the broadcast address. So these two addresses cannot be used. So this is the first example that we have covered in this particular practical session. And now we will cover next example, that is example 2. So let me remove this whole drawings. So example 2 is create a dedicated subnets for data center network, specifically for web servers, app servers, and DB servers. So we have to create subnets for data center network. So you can, okay, so next, so we have to create subnets for data center network, and we have to create subnets for web server subnet. Then next one is app server subnet, and next, for the next one is DB server subnet. So data center network, so initial data center network, let's suppose, has a network address of 10.0.0.0/16, and we have been asked to create subnets for this particular, we have been asked to create these below subnets. The initial data center network is 10.0.0.0/16, and the number of IP addresses which are assigned for data center network is, so this is the subnet mask, which is network ID. The number of hosts is equal to 2 raised to the power of h minus 2. So 2 raised to the power of 16 minus 2. So this value comes as 65,700 and something. So around 65,000 IP addresses you have in your hands, and out of that you need to create subnets for this particular three. You need to create these three subnets. So we'll consider, let's suppose, this web server subnet requires around 255 addresses. Then app server subnet requires 128 addresses, and like database server has a requirement of like 64 addresses. So in that case, what we can do is we can use the readily available CIDR notations which can fulfill these requirements. So these are the requirements for these subnets: 255 addresses, 128 addresses, and 64 addresses. And to fulfill these requirements, we can use the uh, subnet readily available subnet masks or CIDR notations. So If we consider CIDR notation of slash 30, so how many hosts that can be created? So 2 raised to the power of 2 minus 2. So 4 minus 2 is equal to 2. So this is the minimal. So 2 hosts can be created using CIDR notation slash 30. So we'll further see how many can be created with 29 CIDR notations. So 2 raised to the power of 39. So 32 minus 29 is equal to 3. So 2 raised to the power of 3 minus 2, which is nothing but 8 minus 2, 6. So slash 29 with slash 29 CIDR, we can create 6 hosts slash 28. So 2 raised to the power of 32 minus 28 is equal to 4. 2 raised to the power of 4 minus 2. So 16 minus 2 is equal to 14 hosts can be created. Slash 27 slash 26 slash 25 and slash 24. We'll see till 24. So 2 raised to the, so 32 minus 27 is equals 5, and 2 raised to the power of 5 minus 2 is nothing but 32 minus 2 is equal to 30 host or IP addresses. Then 26 minus 20, 32 minus 26 is equal to 6. 2 raised to the power of 6 minus 32 is equal to 64 minus 2 is equal to 62 IP addresses. 2 raised to the power of 7 minus 2 is equal to 128 minus 2 is equal to 126 IP addresses. 2 raised to the power of 8 minus 2 is equal to 256 minus 2 is equal to 254 IP addresses. 32 minus 25 is equal to 7. 32 minus 24 is equal to 8. And here you can see these are the readily available CIDR notations or subnet masks that we can use to fulfill these requirements. So if in our example we have a requirement of 254 5 addresses, that is we can use slash 24 subnet. So we can use a slash 24 subnet for web server subnet, or we can use a slash 24 CIDR notation for web server subnet. For app server, we have a requirement of 128 addresses, which can be fulfilled with 20 slash 25 CIDR notation. And DB server subnet has a requirement of 64 addresses, which can be fulfilled with slash 26 CIDR notation or slash 26 subnet. So how can we create a network using these CIDR notations that we will see now? So first, network or web server subnet will have a web server net subnet will have a address range starting from 10.0.0.0 till 10.0.0.255. So this is the first. This is the address space for web server subnet. This is the network address. This is the broadcast address. Similarly, for app server subnet, we can use the subnet starting from 10.0.1.0 and 10.0.1.128. So 127, it would be 127. So this is the address space for app server, and 10.0.1.128 till 10.0.1.191. So here you can see in first, like for first network, we have completely used the, so first subnet has completely used this network 0 network, this completely used 0 network, and next network started from 1. So similarly, further requirements for within data center, the networks will get added from 10.0.1.192, starting from 192, it will create new subnets in this particular data center. So this is the example 2 of this subnetting topic. The example 3 is create a subnets for ISP network. This subnetting concept is useful, and this is required when you are working as a DevOps engineer or cloud engineer or network engineer. Without this, you can't really work in cloud or in any infrastructure. So you should have a clear understanding on this particular topic. If you have any queries related to subnetting or IP addressing, feel free to post your queries in comment section. I will be happy to answer your queries and questions. And see you all in the next topic of this networking course. So the next topic that we are going to cover in this particular networking course is ports. So ports are nothing but a logical endpoint for communication in the network. It is generally used with IP addresses to identify specific process or service running on a device. So let's suppose you have a virtual machine and you are running Apache service. So in order to connect to that Apache service from outside the VM, we need some kind of endpoint, and that endpoint is represented by port. So each service running in Linux which is exposed to the outside world will have port, and these ports are managed by an organization named as INA. So INA stands for Internet Assigned Number Authority, which is responsible for maintaining official assignments of port numbers for specific uses. The types of ports are divided into three categories: well-known ports, registered ports, and dynamic ports. So ports starting from 0 to 1023 are reserved ports, and you cannot really use these ports for your personal use or for your applications. So commonly used protocols from this range is HTTP, which runs on port 80, FTP, which runs on port 21, DNS service, which runs on port 53, and SSH service, which runs on port 22. So these are commonly used services in cloud. Second type of port is registered port. So port number range starting from 1024 to 49151 is used by applications or services, and any developers, or we can use these ports for our purposes, for our internal purposes, or for running our applications. If we want to use these ports officially, then organizations can ask to INA and they can register ports from this range officially. Next type of port is dynamic port, and it ranges from 49,152 to 65,535. And these are ephemeral ports or private ports, which are used specifically for temporary or short-lived connections. Then we also have a concept called as socket address. So socket address is nothing but a combination of IP address and port number. So what are the importance of ports? So for identification of services and scalability of services, you need ports. In microservices architecture, you will run thousands of microservices, and those microservices will have certain ports in order to connect to those microservices. So it provides these ports provides identification of those services and scalability of those microservices, which is the main usage of this port. And ports are very much required when you are working in microservices architecture. Ports enable efficient data routing, and in order to block traffic from specific applications or services, we can make use of these ports. So when you are working in cloud, you will bound your traffic based on these ports. So let's suppose you have created a virtual machine in cloud, and you want to allow external traffic to be connected on specific port or specific endpoint. In that case, you will enable that specific port on firewall level or NSG level, network security group level, so that only that port will able to so with that port so only that port will be allowed to access those VMs. So this is a high level overview of ports. Next topic that we are going to cover in this particular course is protocols. So what is protocol? Protocol is a set of rules that define how data is transmitted over the network. Protocols determine how communication happens, including structure of messages, error handling, and how devices on the network should respond to various events. Some commonly used protocols are HTTP, HTTPS, TCP, UDP, DNS, etc. As a DevOps engineer, you closely work with protocols like TCP, HTTP, and DNS. So next thing we are going to cover in this particular course is how TCP works, how HTTP works, how DNS works. So first thing that we are going to cover how TCP works. TCP is a reliable connection-oriented protocol that ensures data is transmitted accurately in order without loss or duplication. Here is a simplified breakdown of how it works. So in TCP, connection establishment is the first step and it follows three-way handshake. So TCP follows client server architecture, and when client wants to communicate with server, it first sends sync package to the server. When server receives sync package from the client, it sends sync acknowledge package. When server responds with synchronized acknowledgement and client receives that acknowledgement, client sends back the acknowledgement to that server's response, and then the connection gets established. So first client sends sync packet, then server sends back sync along with acknowledge packet, and then client further send acknowledge packet. And here the connection establishment is done, and further data transfer can be done from client to server. So when client sends data to the server, the data or the input data is divided. The input data gets divided into segments, and each segment contains a header with control information like source and destination ports, sequence number, acknowledgement number, etc. A payload with actual data. So segment has header and a payload. So payload will store the actual data. So in our case, that is iPhone, which user wants to search it on Amazon website. So actual payload will be the text that has been passed as an input, and acknowledgements are sent back to confirm that the data is received. And TCP ensures retransmission of lost and corrupted packets that are present while data transfer. So this is the second step in the TCP, which is nothing but a actual data transfer between client and server. Once the data transfer is done, in order to terminate the connection that has been established using three-way handshake. So for connection termination, in order to terminate TCP connection, it makes use of four-way handshake process. So client first sends finish packet to the server, that is fin packet. Then server receives that fin packet and sends fin plus acknowledge packet. So finish acknowledge packet is further sent to the client. Client receives that packet, then server further sends finish packet, and client receives this finish packet, and then client further sends finish acknowledge packet, and the server then receives that finish acknowledge packet, and here the connection gets terminated, which was established using three-way handshake. So this is the overall process that is being followed in TCP. Next thing that we are going to learn is how HTTP works. So HTTP stands for Hypertext Transfer Protocol, and it is used at layer 1 of OSI model, that is application layer. This protocol is used for transferring data over the web. HTTP defines how messages are formatted and transmitted between a client, which is nothing but a browser, and a server. So transmission between client and server is managed using HTTP. And to transfer data over the web, we make use of HTTP protocol, and it runs on port 80, and the secure version of HTTP runs on port 443. So here is a simplified overview of how HTTP works, and it follows request response model. So first thing is client request. So client sends a request by entering URL in the browser, and it creates an HTTP request and sends it to the web server. So in our OSI model example, we have seen that user enters a URL in browser, and browser is responsible for translating that URL into HTTP request. Then further, that HTTP request is sent to the web server. Web server is responsible for processing that user request, and it retrieves required files from the database. So once the processing is done for the user request, some results will be generated at web server end, and those results of that search, or those results of that input data, will be sent back to the user. So in HTTP response, it sends search status as well as web page data. So web server prepares a response in such a way that it adds it adds HTTP headers with status code and the actual response data, uh, which needs to be rendered on user browser. Further data is sent to the user browser, and that data is being rendered, and user will be able to see the web page of requested data, that is iPhones. So the user will able to see the list of iPhones as the response data. So in this HTTP like request response process, the client first sends the request by entering the URL, and the request is transformed by browser. So that request contains HTTP method, requested resource, that is index.html or search.html page in our case, then HTTP version, headers and body is being sent to the web server. Then server process receives that request, process it, and then sends a HTTP response back to the client. The request contains the response contains below things. The response contains below things: status line, headers, and body. So status line contain HTTP version, status code. Headers contain content type, content length, cache info. Body content response data like HTML page, images, etc. So this is how HTTP works. Commonly used HTTP methods are as follows. HTTP makes use of below methods in order to operate on input data. So first method is get. So in order to retrieve data from the server, get HTTP method is used. In order to post data to the server, it makes use of post method. In order to update or create data on the server, it makes use of put method, and in order to delete data on the server, then it makes use of delete HTTP method. So these are the HTTP methods that are being used to perform crude operations on server. Then some key HTTP status code are as follows. So whenever we request anything to the server, some response is generated and sent back to the user. So when you type any random things in the URL of the browser, you will get a 404 error, which denotes that requested resource is not available. This requested resource is not found. When HTTP status code is 200 OK, that means your success request is successful and your content is returned back to the browser. 500 internal server error is nothing but server encountered an unexpected condition. So if your server itself has some issues, in that case you will get this error. And these are the commonly used status codes that you should know when you are troubleshooting some microservices based application. So as a DevOps engineer, you should know these HTTP status codes. You should know all these HTTP methods. So this is all about how HTTP works. Next topic that we are going to cover is how DNS works. So DNS stands for domain name system, and it translates human readable domain names into IP addresses. So IPv4 supports around 4 billion IP addresses, and in order to remember any of the IP addresses, it is not possible. So we have domain name system which translate any domain name into IP address that computers use to identify each other on the network. And how DNS works? So it starts with when you type URL in the browser need to find its corresponding IP address. So it checks that info in the browser cache, OS cache, and router cache. So browser first check whether, let's suppose you want to search google.com, you want to open google.com website, and you typed in the URL section, you have typed in www.google.com, and so that particular so it checks whether the entered URL is present in browser cache or OS cache or router cache. If the entry is not present, then the request will be further sent to DNS resolver. So your computer sends a query to a DNS resolver, usually provided by your ISPs or public DNS services like Google DNS. The DNS resolver is responsible for finding the IP address. DNS makes use of recursive lookup process. So if the resolver doesn't have IP cached, it starts a recursive lookup. So DNS resolver also maintains some cache in order to store widely used or mostly frequently used DNS entries. And if the entered URL or entered domain is not present in DNS resolver itself, then it follows recursive lookup process. And in recursive lookup process, it starts from its first request. So DNS resolver will first send request to DNS root server, and it will ask for top level domains. So these are the top level domains that are commonly used, like .com, .org, .edu, .da, .ch, .uk, .au. So these are categorized based on different things, like these are generic domain names. .com, .org, .edu are generic domain names. .da, .ch, .uk, these are country code domain name servers. So our let's suppose you are searching amazon.com. So amazon.com is a part of this top level domain. .com top level domain. So this is TLD for our domain, that is .com, and the local domain is Amazon. So it first queries the DNS resolver first queries to DNS root server, and it asks for this. It asks for top level domain for your entered DNS address, that is amazon.com, www.amazon.com. Then TLD server points to the authoritative name server for example.com or for amazon.com. So let's suppose .com is the top level domain, and this top level domain further send that request. So DNS root server will send our request to .com top level domain. Then this top level domain server points to name server, authoritative name server, which is amazon.com, and this authoritative server points responds with IP address for Amazon, responds with IP address for amazon.com. So this will further send the response back to DNS resolver, and DNS resolver will send response back to the requester or user. Once the authoritative server responds with IP address for amazon.com, the caching process starts. So the the IP address will be first sent to DNS resolver, and from DNS resolver it will be sent to user, and user will able to then uh, load, and based on that IP address the website will be rendered to the user. So it also performs the caching process. So DNS results are often cached at different levels. So once you open amazon.com on your computer or in your browser, so the IP address will be stored at different levels. So that domain name entry will be stored at browser level, OS level, and whenever you open like number of websites on your, like, so on day-to-day basis, whenever you open thousands of websites on your browser, all those website all those websites domain entries will be stored in your browser cache or in OS cache. So whenever you open any of the website from those thousands of website, then in that case it will be that website will be fetched quickly, because the entry will be found at cache level itself. So for speeding up future request for the same domain, caching is done, and DNS makes use of port number 53, and from transport layer protocol it makes use of UDP in order to perform DNS queries. So this is the high level overview of how DNS works. Now let's see the commonly used DNS records. As a DevOps engineer, you will interact with these records when you are dealing with DNS servers. So first record is a record which maps a domain name to an IPv4 address. Second name record is 4-time A record, which maps a domain name to IPv6 address. Third record is CNAME record, which create an alias of one domain to the other. Then fourth one is MX record, which specifies mail servers. Fifth one is NS record, which is a name server record, which specifies authoritative DNS servers for a domain. And last one is PTR record, which maps an IP address to a domain name. So this is the high level overview of how DNS works and commonly used DNS records. The next topic that we are going to see is Azure Cloud Networking Components. And here is the list of commonly used Azure Cloud Networking components. So first one is virtual network. So virtual network in Azure provides a private network which enables communication between resources. So you want to create, so whenever you create a subscription in Azure, you will need to create virtual network, which will act as a private network for your whole subscription. And in that virtual network you can create as many subnets as you want, and that virtual network will represent your uh, virtual private cloud. So it will represent your network, your organization network. So similar resource in AWS is virtual VPC, that is virtual private cloud. So in Amazon we create VPC, and similarly in Azure we create virtual network in order to create a network for your whole organization. Second resource is subnet. So in order to divide your large network into smaller subnetworks, we use subnets, and subnets is a resource that is provided in Azure. So with help of subnet you can divide your virtual network into smaller sections, uh, and those subnets can be used for isolation and security. Third thing, third resource in the list is network security groups. So if you want to restrict incoming and outgoing traffic for your subnet or for your virtual machines, in that case, you can create network security groups. Fourth resource in the list is VPN gateway. So if you want to set up a connectivity between your on-premise network and your Azure network, in that case, you can set up a VPN gateway. One other resource that also provides a dedicated connectivity from your Azure cloud to your on-premise network is ExpressRoute, which is the second last component of this particular list. Next resource is Azure Firewall. So if you want to set up a firewall uh, for your whole network, in that case you can go with Azure Firewall. And Azure Firewall is fully managed network security service provided in Azure, through which you can manage the traffic and you can restrict the traffic. You can monitor the traffic and you can restrict the traffic based on your requirements. Then we have Azure App Gateway and Azure Load Balancer. So Azure App Gateway is layer 7 load balancer for HTTP and HTTPS traffic. So if you have any applications that are being set up in Azure, so you can use Azure App Gateway to load balance to perform load balancing for your applications. So Azure App Gateway will load will so through Azure App Gateway you can easily load balance your HTTP and HTTP based traffic. Azure Load Balancer is the standard load balancer uh, used for load balancing the normal traffic. So Azure App Gateway is Azure App Gateway works at layer 4. Sorry, Azure App Gateway works at layer 7 of the OSI model, and Azure Load Balancer works at layer 4 of OSI model, that is transport layer. So it deals with TCP UDP based traffic, and it is widely used when you are dealing with other networks. Express route, similar like express route again is used for connecting your on-premise network to other network. And a Azure Bastion is a VM that is created. So Azure Bastion service, through Azure Bastion service you can communicate to your Azure network through SSH and RDP ports uh, in a so Azure Bastion is a dedicated service through which uh, your you can connect to your VMs inside Azure network. So this is, you can connect. Azure Bastion is a dedicated service through which you can connect to your VMs. You can connect to your VMs in Azure network. It provides SSH and RDP connections in order to connect to that Azure Bastion system. And from Azure Bastion, you can connect to any of the VMs. So this is the like high level overview of Azure cloud networking components. We are going to cover all these components in a detailed manner and in a practical way when we are going to cover cloud networking course. For now, this for now we have just covered a theory part of these components for to learn the basics of networking. We have just mentioned only few components that are required on a daily basis. Here you can see hub and spoke model. So this is the high level representation of hub and spoke model, and we have referred this image from Microsoft Learn website. And here you can clearly see that Azure Virtual Network Manager, inside Azure Virtual Network Manager, we have one VNet which is dedicated for hub, and all the different VNets that are created inside this VNet manager are spoke networks. So in hub and spoke model, we will have only one hub and multiple spoke, and these multiple spoke networks will communicate through hub network. So in hub virtual network, you can see all the resources which are common across the network are added inside hub. So through this model, you can save a lot of cost, and this provide a extra layer of security to your organization. So in, you can see here in hub virtual network, we have added Azure Bastion, Azure Firewall, and VPN Gateway. And these are the only three resources which are being accessed throughout the organization. So this particular organization has production spoke where different subnets are created to spin up virtual machines for different departments. So here you can see two production spoke models, two production spoke networks, and two non-prod spoke networks. And these all subnets are paired through VNet peering. So Azure also provides one more networking component, that is VNet peering, through which virtual networks can be connected. So non-prod VNets are paired through VNet peering, and all the spoke networks are connected to this hub network, and they are accessing all these resources for their use. So we have like VPN gateway, Azure firewall, and Azure Bastion, and all these components inside hub are monitored through Azure Monitor. So diagnostic for Azure Bastion is monitored inside Azure Monitor. Then Azure firewall is accessed in, here you can see Azure firewall is accessed in production environment. VPN gateway is also monitored through Azure Monitor, and VPN gateway is accessed in this non-prod environments. And this whole hub virtual network is secured with DDoS protection. And all these uh, spoke networks are connected to hub using tunnel. So post tunnel, you can see it here, and VNets are connected and paired through hub. So all the VNets are connected and paired through hub. So for pairing, VNet pairing is used, and this is all about hub and spoke model, which is represented here. So based on networking concepts that are being presented in this particular course, you can easily understand what all things are going in the networking. You can easily understand and create this kind of like architectural diagrams for your own network, or based on requirement you can design such kind of like uh, diagrams for your network. So this is the last chapter. Thank you for joining us on this exciting journey to learn complete networking from scratch. Let's quickly recap what we have covered in this entire course. First, we have started with OSI model and TCP/IP model. In that, we have covered a real-world example showing how OSI model works in a real-time scenario. Then we have covered overview of each layer in OSI model and TCP/IP model. The second topic that we have covered was IP addressing. In that uh, we have gone through what is IP address, what are the classes of IP classes, and we have seen the IP address representation in various format like dotted, decimal, binary format. In third chapter, we have seen networking subnetting concepts, and we have gone through important definition, key terms of subnetting, and then we have seen the practical example of subnetting with some real world examples. Fourth topic we have covered in this course was ports. There we have learned about basic definitions of ports, then types of ports. We have seen importance of ports. The fifth topic was related to protocols. Under that we have learned introduction to protocols, how TCP protocol works, how HTTP protocol works, how DNS protocol works, and their equivalent real-time examples. And last topic we have covered Azure cloud networking components, and there we have learned commonly used networking resources, and we have gone through hub and spoke model. So this is the entire course summary which we have covered in this complete networking course from scratch. This was just the beginning. Networking is the first subject in our complete DevOps roadmap, and you have now built a solid foundation to move forward. Up next, we will dive into Linux operating system, where we will cover Linux basics, file management, user management, package management, disk and service management, and scripting for automation. We will see how Linux is useful for modern DevOps environments. If you have enjoyed this complete networking course from scratch, then please like this video to show your support. Subscribe to our channel so you don't miss the next part of DevOps roadmap, and comment below with your feedback on or any topics that you would like us to cover. Keep learning, keep growing, and we will see you in the next course, that is Mastering Linux for DevOps. Thank you and take care.